Chapter 8 in class exercise 2, problem 8.92. Determine the force P that must be applied to the handle of the lever so that the wheel is on the verge of turning if moment applied is 300 Newton meters. So that's moment M is given as 300 Newton meter. The coefficient of static friction between the belt and the wheel is 0.3. So this problem is also similar to the problem of in class exercise 1, but now we have addition of belt into this problem. So we need to apply the concept of friction in the flat belt. So similar to the previous problem, there are two parts or two physical objects here, the rotating wheel and then the lever. So first let's draw the free body diagram for the wheel. So this is the center point of the wheel, which is the pin, and pin has support reaction Bx and By, and these are directions are our assumption. Okay, we are assuming the directions for them. Now the belt, when the lever force is applied onto the lever in the downward direction here, it pulls the belt on at D. So tension at D is more than tension at C. So let's add them here. So this is TD and this is TA. Remember, we always saw the tension in the belt or rope going away, not towards the rope. So this is TDTA. Those are the forces, and then the belt is in contact with the wheel for this angle, all the way from here to here, and that's beta, which is 270 degrees. So we will convert this into radians before we substitute that into the equation, and then the wheel is subjected to counterclockwise moment of 300 Newton millimeter, which is 0.3 Newton meter. Oh, sorry, it's 300 Newton meter only. Sorry, so I thought it's millimeter. It's 300 Newton meter only for the moment. Okay, so those are the different forces and externally applied moment. Now, if the system is in equilibrium, then we can apply the equation for the sum of moments. But before that, we need to know the relation between TD and TA, and for that we apply the equation of flat friction forces in flat belt. So beta is 270 degrees, which is 270 multiplied by pi by 180 radians, and then we can write down this equation. TD divided by TA is e to the power mu beta. Now TD is more, that's why TD is on the numerator and TA is in the denominator. And now it's time to substitute the numbers here. So e to the power 0.3 multiplied by this whole thing is 3 pi by 2. So when exponential to that power is calculated, it comes out to be 4.112. So TD is equal to 4.112 times TA. So TA is now multiplied on the right side of the equal to sign. So let's call this equation number 1. And then we can apply sum of moments about B, which is the center of the drum. This is B. Now why B? Because we would like to eliminate two support reactions that we don't know, Bx and By. So now it's only TA and TD and externally applied moment. So we can, and that is equal to 0 when the system is in equilibrium. Counterclockwise is positive. So externally applied moment at B plus TA multiplied by 0.3 minus TD multiplied by 0.3. So TA results in counterclockwise moment, TD results in clockwise moment is equal to 0. And this number here is 300. So it's 300 plus TA times 0.3 minus TD times 0.3 is equal to 0. Now we can substitute TD in terms of TA into this equation. So we can, instead of TD, we can write 4.112 TA. So everything is in TA. So substituting TD is equal to 4.112 TA, and solving for TD and TA respectively. So we get TA is equal to 321.4 newtons and TD is 1321.4 newtons, and TD is more than TA. Okay, so by drawing free body diagram for the wheel, we have solved for TD and TA. So now what we do is we transfer those forces onto the lever, because the other ends of it's the same belt that is attached to the lever, so it's the same tension but in the opposite direction. So this is TD and this is TA. And here the pin is C, so there are support reactions CX and CY, and here is the externally applied force on the lever. So this is for the wheel and this is for lever. Free body diagram. Okay, so we can now focus on this part of the solution. Let's actually move this here. So this is TD and this is lever. Okay, so what we need to do now is we are calculating P based on the values of TA, TD, and the distances that we have been given. So this distance is 0.7 meters. Oh, that's up to point C. So this distance from C to P is 0.7 meters. From C to D, this is given in the problem as 0.025 meters. Okay, this distance between C and line of action of D, and between C and A, this distance is 0.06 meter. This is 0.06. Okay, so now we can apply the sum of moments equation at C is equal to 0 when the system is in equilibrium. Counterclockwise is positive. Again, why have we selected C? Because we would like to eliminate CX and CY. So now it's because of TD and C. So it's counterclockwise. TD multiplied by 0.025 minus TA multiplied by 0.06. So that's clockwise, that's why negative, and P is also clockwise. So P is the moment of P about C is clockwise as well. So it's negative P times 0.7 is equal to 0. Okay, so let's look at it. Yeah, that's correct. Okay, and when we solve this problem, we can substitute the value of TA and TD from here. So we already have calculated those numbers. We can substitute these values here, and then we can solve for P, and P is 19.6 newtons. 19.6 newtons. So the question is, determine the force P that must be applied to the handle of the lever so the wheel is on the verge of turning. Okay, so that force is 19.6. Okay, and that's our entire solution. Thank you.